Hi Chem 101 students, and welcome to week 12. We've got two video lectures this week. The first one's about intermolecular forces, and the second one is about the consequences of these intermolecular forces. So we'll begin to talk about those in this lecture as well. First, I'm going to do a little bit of a review of bond polarity, because that will be really important here. And we're going to use our knowledge of Lewis structures, VSEPR and molecular geometries, and bond polarity to determine whether an entire molecule is polar. This is going to be very important because the attractions between molecules are going to depend very much on whether the molecule is polar or not polar as a whole. And this not only depends on the fact whether or not it has polar bonds, but also the way in which those polar bonds are arranged in the molecule. And so we'll have to be able to visualize the three-dimensional structure as well. And so a lot of this week's practice is going to be more about drawing Lewis structures, looking at the shape, and using all of that to determine the polarity of the molecules. So just a reminder, bond polarity means unequal sharing of electrons within a bond. The way you determine if a bond is polar or not is you take the difference in electronegativity between the two atoms in a particular bond. And if the electronegativity difference is 0.5 or greater, we consider that bond to be polar. And so if you have a molecule that has only a single bond, a diatomic molecule, for example, let's say this molecule here is fluorine attached to fluorine. So I talked about this a little bit last time, and we now know about how to draw Lewis structures and stuff. Here's the Lewis structure. If we draw F2, fluorine gas. Now, if we look at fluorine, fluorine has an exceptional electronegativity, 4.0. It's the highest. However, this molecule is not polar because there's only one bond in the molecule, and here the electronegativity for fluorine is 2, or is 4.0 for this fluorine here, and 4.0 for this fluorine. And so neither of the fluorines can pull the electrons away from the other, even though they both pull very, very hard on electrons. Because each one pulls just as hard, it's like a tug-of-war. So if you see, let's say you ever went to I don't know, you ever did a tug-of-war. It's not something people do very often these days, but let's say you go to the park and you see people having a birthday party or something, and they got a tug-of-war. And you see this big giant guy, really buff, pick up one side of the rope. And you think for sure he's going to win this tug-of-war. But then his twin brother, who's just as buff and huge as he is, picks up the other side. And now you're not so sure. Who's going to win the tug-of-war, because they're both pulling in opposite directions with equal strength. Yes, they're both very strong, but the rope isn't going to move anywhere because they're both equally strong. So that's the way it goes in bonds as well. If both atoms are equally strong here, then neither will be able to pull the electrons away from the other, and the electrons are like the rope. The electrons won't go anywhere, just like the rope wouldn't go anywhere. Now, this is a pretty simple matter when we just have two atoms in the molecule. But what if we have many atoms in the molecule? Well, that's where things are going to get more complicated, and that's what we're going to work on here. Here's an example of a molecule here, like let's say HCl or HF. Here the electronegativity for the chlorine is like 3.2, and for the hydrogen 3.2, and for the hydrogen it's like 2.2, I think. Let's see. 2.2 and 3.2 for the chlorine. So the difference is 1.0 here. So this is definitely a polar bond. So this molecule, which only has the one bond, is an extremely polar molecule. And so in this molecule, the electrons are spending more of their time around the chlorine and less of their time around the hydrogen. So chlorine's the big buff guy pulling the rope his way, and hydrogen is missing out on those electrons. The result is that the chlorine side of the bond is partially negative, which we can indicate with this lowercase Greek delta and a negative sign. and the hydrogen side of the bond is partially positive, which we might indicate with the lowercase Greek delta and a positive sign there. These are partial charges, so meaning they're not full charges. The chlorine doesn't have one full negative charge, nor does the hydrogen have one full positive charge. These aren't ions when they're in this molecule anyway, not when they're in the molecule. In water, if it were HCl, it could break apart, but that's a different situation. Here we have a partial negative charge in the chlorine, a partial positive charge in the hydrogen. And so when you have a single bond in a molecule, it's pretty easy to see if the molecule is polar or not. You just see, is the one bond in that molecule polar? But if we have a more complex molecule with many, many bonds, there's going to be a lot of pulling and tugging of electrons in various different directions. And so in that case, when we have a more complicated molecule with more than one bond, we have to think about not only is the bond in the molecule polar, but is the net result of all the pulls of all the different atoms in the molecule pulling the electrons more to one side of the molecule than the other, then the molecule overall can be polar. But it takes more than knowing, in a molecule with more than one bond, you have to know more than if the bond is polar. You need to know how the electrons are being pulled around in the molecule. And so to decide if an entire molecule is polar, we actually have to do three things first. And those were the three things that we learned how to do last week. Number one, you've got to draw the Lewis structure of the molecule so you can know what bonds there are in the molecule, what atoms are bonded to what other atoms. Next, you have to use VSEPR to determine the geometry of the molecule, because again, it's not enough to know that some of the bonds in the molecule are polar. We must also know how are they pulling the electrons around in the molecule to know if the electrons are being pulled more to one side of the molecule than to the other, because if they are, that's what will make the molecule polar. Finally, we have to determine if there are any polar bonds in the molecule. And so if the molecule has at least one polar bond, then it may be polar, but that's not enough to make the whole molecule polar. For a molecule to be polar, it has to meet two conditions. Number one, it has to have at least one polar bond. If there's not at least one polar bond, then the electrons really aren't being pulled anywhere in any part of the molecule very hard, and so the molecule overall won't be polar. But if it has at least one polar bond, then we have another condition to meet, because again, you could have various polar bonds in the molecule, but if they're all pulling against one another, they could cancel each other's pulls out. So we have to make sure that the molecule is not symmetrical. So, for example, the shapes that are symmetrical are the tetrahedral shape, the trigonal planar shape, and the linear shape. It's easier to see with the linear shape. If we've got a molecule like CO2, I can draw that very easily on my page here. If I've got a molecule like CO2, it's very clear to see that this is symmetrical. The oxygen is pulling. The oxygen is much more electronegative than the carbon, so this oxygen is pulling electrons away from the carbon to the right side of the molecule here. But the other oxygen is pulling in exactly the opposite direction. So even though carbon dioxide has two very polar bonds, those bonds are positioned directly opposite one another because this molecule is linear in shape. So for a molecule like CO2, we meet the first condition. Does this molecule at least have one polar bond? Yes, it does. But we don't meet the second condition because the molecule must not be symmetrical. But due to its linear shape and the fact that both of these atoms are oxygen, equally strong in pulling electrons, they are pulling exactly opposite to one another. So this is again like the tug of war. The carbon is in the middle of the rope. And the oxygen is one big, buff, huge guy that pulls on the rope really hard, pulls on the electrons really hard. But his twin brother is on the other side of the rope pulling just as hard. So overall, these electrons are neither being pulled to the right overall or to the left. Their pulls are canceling each other out. So again, this molecule is not polar, because it does meet the first condition. It does have polar bonds. The carbon-oxygen bonds are polar, but it doesn't meet the second condition. The molecule is symmetrical. The molecule has to be asymmetrical or not symmetrical in order for the overall molecule to be polar. And this can happen in one of two ways. One, you can have an asymmetrical shape, such as the shapes that aren't tetrahedral, trigonal, planar, linear, such as bent shapes or trigonal pyramidal shapes. Those are asymmetrical. Or you must have a situation where the atoms all around the center are not all the same atom. Because if they're different atoms, then their strengths of their pull will be different. For example, if this were not oxygen, if it were sulfur, that would be a different story because the sulfur doesn't pull nearly as hard as the oxygen. So the oxygen would win out and the electrons would be pulled to the other side. But since the oxygen is on the right side here and the oxygen is on the left side too, they both pull with equal strength. Therefore, the electrons are neither being pulled in one direction or the other. This is fairly obvious to see with a linear molecule. It's a little bit harder to visualize with a tetrahedral molecule because now you have to think of things in 3 dimensions, and that can be difficult. I'm going to close my slides just for a second here because I want to run my little script. I forgot to run it. And that is going to help me. Okay. And so let's take a look at a couple of examples that demonstrate this point. So here we have a molecule representing CF4. So the electronegativity for carbon is 2.5, and for fluorine it's 4.0. So you have 4 carbon-fluorine bonds here. So for a carbon-fluorine bond, it's again 2.5, 4.0. We take the difference, 4.0 minus 2.5. That difference is 1.5. So these carbon-fluorine bonds are very, very polar. So remember, we have to meet 2 conditions. Number 1, do I have at least one polar bond? And the answer is yes, I do. But the second condition is my molecule asymmetrical, meaning not symmetrical? Symmetrical. The molecule must be not symmetrical. However, if you look at the tetrahedral shape of CH4 here in this model, you can see that it is symmetrical. It's the same all the way around. A tetrahedral shape of this kind is completely symmetrical, assuming that all these atoms are the same, which they are. They're all fluorine. So this is also like a tug of war, but it's a 4-way, 3-dimensional tug of war, which is a little bit more difficult to picture and imagine. But you've got 4 big buff guys pulling on the rope. The center of the rope is right here in the middle. It's the carbon atom. So just like we saw with CO2, there were oxygens on opposite side pulling against one another. Here, there's a 4-way tug of war. Instead of 2 ways like with the CO2, it's 4 ways. But you can imagine a 3-way tug of war, because a 3-way tug of war is flat still on the ground. So let's say you had 3 people pulling on the rope and the ropes were all connected in the middle. Again, if they're all evenly spaced in a triangle in a symmetrical fashion, and they're all the same strength, no one's going to be able to pull the rope away from the other. Now, you can't have, on Earth anyway, maybe in space, but on Earth you can't have a 4-way tug of war in exactly the same way, or not on the ground. But it's working exactly the same way because of the symmetry of this molecule. Even though each of these bonds is extremely polar, they're all pulling in equal angles away from each other. So due to the symmetry of the molecule, because this molecule is symmetrical, it's not asymmetrical, it's symmetrical, this molecule is not polar, even though it has very polar bonds. It's because due to the symmetry of this arrangement, the tetrahedral arrangement, these bonds are all pulling in opposing ways from one another. So none of the pulls, all the pulls cancel out basically. And so overall, because we did not meet this second step of asymmetry, not being symmetrical, this molecule is not polar. Now take water on the other hand here, H2O. So you can see this was a tetrahedral shape, which is a symmetrical shape, assuming that all the atoms are the same. The water molecule has a bent shape. Now the electronegativity for oxygen here is 3.5, and for hydrogen it's 2.2. So 2.2, not 2.5. So 3.5 minus 2.2 is 1.3. And so these bonds are very polar as well. So in terms of the first condition, polar bonds, does water have at least one polar bond? And the answer is yes, it does. And the second condition is this water molecule asymmetrical? And the answer is yes, it is, because of its bent shape. So you can see that there's the oxygen side here is different from the hydrogen side. This is the asymmetry of the molecule. And oxygen pulls on its electrons much harder. So the result is that the oxygen side of the molecule is going to have a negative partial charge because the electrons are being pulled in this direction towards the oxygen side of the molecule. And the hydrogen side of the molecule will have a partially positive charge due to the fact that the electrons are being pulled away from the area where the hydrogen is. So the result is that this molecule is polar. This is a polar molecule, water. And it's because it meets both conditions. It has at least one polar bond. Both of these bonds are polar here. And it is asymmetrical. Notice the difference between a molecule that's symmetrical, evenly spaced bonding all the way around all the same atom, and a molecule that's asymmetrical. Notice the difference. This side is different from the other side. That is an asymmetrical molecule. Okay, so all this stuff that we did last week, building up to this, drawing the Lewis structure so that we could use VS-EPR to figure out the shape, also figuring out if bonds are polar, it's all leading up to this moment here, where we can finally decide if a molecule is polar or not simply by looking at the formula. And being able to predict whether a molecule is polar or not is going to allow us to predict many of the properties of these compounds, which is really cool. You can simply, even if you've never seen a compound before in real life, you can, from the formula, determine what kind of properties it's going to have, simply based on your knowledge of chemistry. So let's look at a few more examples, and decide, are these polar or non-polar molecules? Okay, so again, we've got multiple steps to go through here. We have to first do the 3 preliminary steps. Number 1, draw the Lewis structure. Number 2, use VS-EPR to determine the shape. Number 3, decide if there are any polar bonds in the molecule. We have to do all of that before we can even figure out if the molecule is polar. So let's start with NBr3 here. So we're going to have to draw a Lewis structure, so we need to get the valence electrons and the covalence number. Okay, and I encourage you to follow along, have your periodic table next to you. If you need to pause this video and grab your periodic table, go ahead. So here we're going to have 1 nitrogen, and we're going to have 3 bromines. Okay. So look down at your periodic table and see what group is nitrogen in. That will determine the number of valence electrons, right? I'm going to open up mine as well. So here we've got, in our molecule, we've got nitrogen, oops. I have too many PowerPoint slides open. Okay, there we go. All right. So we got nitrogen and bromine. Nitrogen is in group 5. We can number these again if we want. You probably have those notes on your periodic table. So nitrogen is in group 5 and bromine is in group 7. So nitrogen has 5 valence electrons. So 5 valence electrons for nitrogen, 7 for bromine. So 1 nitrogen times 5 valence electrons and 3 bromines times 7, that's 21 for a total of 26. And the covalence number for nitrogen, we look here, each nitrogen atom has 5 valence electrons. You would need 3 more to have 8, so its covalence number is 3. Each bromine atom starts with 7 valence electrons. Each one would need 1 more to have 8, and so its covalence number is 1. We're going to draw a skeleton. We put the atom with the highest covalence number in the middle, and then we put the other atoms on the outside. Then we drop electrons as lone pairs on the outside atoms first till they have an octet. Bromine has 2 electrons in this bond. It will need 6 more to have 8. We're going to put 3 lone pairs on it. And we're going to do that for each bromine here. And now we should count up how many electrons we've put down so far. It is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24 down. We have 2 left out of our 26. Those will go on nitrogen. Okay. And now we should figure out if nitrogen bromine bond is polar. Well, we can also figure out the shape first. Either one. You can do either one first. So here, X equals the number of atoms bonded to nitrogen is 3. And E, the number of lone pairs on the nitrogen, is 1. So X is 3 and E is 1. If you look at your VSEPR chart, you'll find that that results in a trigonal pyramidal shape. And I'm just going to bring that up just to show you guys here. Let's get our VSEPR slide back right here. And just to point out here, your shapes that are symmetrical are the linear linear trigonal planar shapes and tetrahedral shapes. Note that formaldehyde here is not symmetrical because the oxygen is different than the other atoms, but assuming that they're all the same atoms, it would be symmetrical. These other shapes here, bent, and trigonal pyramidal, these are asymmetrical shapes. You can see that one side of the molecule looks different from the other. They're not the same all the way around like the tetrahedral shape or the linear shape. This trigonal planar shape would be symmetrical if this atom were the same as the other ones, but it's not in this example. But these ones, even if the atoms are all the same, you can see that the shape itself is asymmetrical. One side of the molecule looks different from the other. It's not the same all the way around. So we're trigonal pyramidal in terms of shape. So we've already evaluated then. We can look at our two conditions here. Remember, the two conditions are do we have at least one polar bond? That's condition 1. Condition 2 is is the molecule asymmetrical? So because it's a trigonal pyramidal shape, this is an asymmetrical shape, and so we've got that second condition down. Now we just have to decide, do we have at least one polar bond? And so our bonds here are nitrogen to bromine bonds, and so we'll have to look up the electronegativity values for that. And so here If we look up our electronegativity values, we see that for nitrogen, they're 3.0, and for bromine, it's also 3.0. They have the same electronegativity. So 3.0 for nitrogen, minus 3.0 for bromine, that is 0.0. These bonds are completely non-polar, so we don't meet the second condition. So this molecule overall is not polar, because although it's asymmetrical, it doesn't have any polar bonds. So the molecule is not polar overall. Okay, remember, we have to meet both conditions. We have to at least have one polar bond, and also the molecule must be asymmetrical. So although this molecule was asymmetrical, it was not polar because it didn't have any polar bonds. Okay, and then I'm going to go back here to a structure we actually drew last week, but I'll quickly draw it again real quick. Valence electrons, covalence number. We got 1 carbon, we got 4 hydrogens, and we got 1 oxygen. So this one was on the homework last week. And let's see, for carbon is group 4, hydrogen is group 1, and oxygen is group 6. So each carbon has 4 valence electrons, each hydrogen has 1, and each oxygen has 6. 1 carbon with 4 valence electrons, that's 4 from the carbon. 4 hydrogens, each with 1 valence electron, that's 4 times 1, 4 from the hydrogen. 1 oxygen with 6 valence electrons, that is 6 valence electrons. So altogether we have 14 valence electrons for this molecule. And covalence number, again, we look right here. So since each carbon starts with 4 valence electrons, it would need 4 more to have 8. And so the covalence number is 4. For hydrogen, it's always 1, because hydrogen can only take 2 electrons. It starts with 1, but it only needs 1 more to fill its shell, because it's hydrogen. It only takes 2, so its covalence number is 1. Oxygen starts with 6 valence electrons. It needs 8 to fill its shell, so it would get those by making 2 bonds. Now, we draw our skeleton, and what we're going to find with our skeleton here is that, well, we have a carbon, and we can start to put atoms around it. Hydrogen, hydrogen, hydrogen. But if I try to put the hydrogen here, then I've filled up my carbon. So I must have an oxygen right there. So I have a molecule with more than one center atom. So here, I could move, now I should start to think, where should I put the hydrogens? Should I put them all on the carbon like this, or should I put some on the oxygen? And the way to decide that when you're making your skeleton is to look at the covalence numbers and try your best to match them as best you can. So carbon is making 4 bonds already. The oxygen wants to make 2, so the last hydrogen we have, we can put it on the oxygen like that. And now we should see how many electrons that we put down. We put down 2, 4, so 2, 4, 6, 8, 10. So we put down 10 electrons. We have 4 more left to put down. We won't put any on the carbon because the carbon already has 8 around it. And we won't put any on hydrogen because hydrogen's filled with 2. So the only remaining atom that could get them as lone pairs is the oxygen, which is good because it gives the oxygen an octet. And so now we have a good structure. We have 14 valence electrons. Carbon's making 4 bonds, oxygen's making 2. Everyone has an octet. So now we have a molecule with more than one center atom. So we can figure out the shapes around each center atom. For carbon here, X is 4, E is 0, and for the oxygen, here, X is 2 atoms bonded to oxygen, carbon and hydrogen, and E is 2 lone pairs. So remember, when you have more than one center atom, you have to do VSEPR for each center atom. And when X is 4 and E is 0. That's X plus E is 4, E is 0. You have a tetrahedral shape. So the carbon shape is tetrahedral around the carbon, and around the oxygen, it's X plus X is 2 and E is 2. So X plus E is 4 and E is 2. That gives you a bent or angular shape. Right. And so none of these are symmetrical really in any way, because although the carbon has a symmetrical shape, it's not the same atom all the way around. Oxygen is definitely a different pull of electrons than the hydrogens. So it's asymmetrical around the carbon. It's also asymmetrical around the oxygen because it has this asymmetrical bent shape. So in terms of our conditions for polarity here, again, we need to know, does it have polar bonds? At least one polar bond. And number two, is it asymmetrical? So we've already figured out this molecule is asymmetrical. Nice. So now we just have to decide, are there any polar bonds? You only really need one polar bond. And I'll just tell you here, and you should be able to figure this out for all of them, but the oxygen-hydrogen bond is super polar. The electronegativity for oxygen is 3.5, and for hydrogen it's 2.2, so the difference is 1.3. So the oxygen-hydrogen bond is polar. The carbon-oxygen bond is also polar. We've got at least one polar bond though, so we are meeting both conditions. Here, this molecule is polar. And it's going to be polar such that the oxygen has the partial negative charge because it's going to be pulling electrons from the carbon. It's going to be pulling electrons from the hydrogen. The hydrogen part and the carbon part will be partially positive. The oxygen, that's the biggest, meanest electron puller in this molecule. So it's pulling the electrons towards itself. And now for the last one, SiCl4. Okay, so SiCl4, let's get the Lewis structure for that. Again, we gotta get the Lewis structure. We've got to find the shape, and we got to figure out if there are any polar bonds. We have one silicon, and we have 4 chlorines. And so silicon is, if we look here at our periodic table, silicon is in group 4, so it has 4 valence electrons, and chlorine is in group 7, 7 valence electrons. So one silicon with 4 valence electrons, 4 chlorines, each with 7. So 1 times 4, we got 4 valence electrons from the chlorine. 4 times 7, we got 28 from the 4 chlorine atoms, for a total of 32 valence electrons. And covalence number for silicon, again, we look at each atom right here. Silicon starts with 4, needs 4 more to have 8, so its covalence number is 4. Chlorine starts with 7, needs 1 more to have 8, so its covalence number is 1. For that reason, we put silicon in the middle and chlorine around the outside. And then we drop lone pairs around the outside atoms of chlorine until they all have an octet. And now this is actually 32 electrons. All the chlorines have an octet. All the silicon has an octet, 4 bonds around it, and silicon's making 4 bonds, chlorine's making 1. This is a good structure. Here for the silicon, we have X equals 4. 4 atoms bonded to silicon, 4 chlorines. E equals 0. Okay, so this is a tetrahedral shape. In terms of polar bonds, the silicon-chlorine bond, silicon to chlorine, let's look at the electronegativities there. For silicon, the electronegativity is 1.9, and for chlorine, it's 3.2. So 3.2 for chlorine, 1.9 for silicon. So the difference is 3.2 minus 1.9. It is a huge difference of let's say 1 point, or pretty big, 1.3 is the difference. So these are definitely polar bonds. So in terms of our first condition, do we have any polar bonds? The answer is absolutely. We have a very polar bond here. Condition number 2, is the molecule asymmetrical? And the answer is no, it is not. It is symmetrical because it's tetrahedral in shape and all the same. The atoms are all the same all the way around. So if we were looking at shapes, it would look like this one right here. It's silicon in the middle, and then chlorine's all the same or on the outside. The tetrahedral shape is symmetrical, assuming all the atoms are the same. So because this molecule is symmetrical, the poles by the chlorine cancel one another out, and so this molecule is not polar. And so that's how we determine if a molecule is polar or not. And the question is now, well, why do we care? Why do we care if the molecule is polar or not? The answer is because that's going to decide the way the molecules attract to one another. And that's going to tell us a whole lot about the properties of the compound made up of those molecules. So here we're going to talk about intermolecular forces next. And I think that's I'm going to call it for this video. For the next video, we're going to determine the result of these polarities and what intermolecular forces they have due to these to the fact whether they're polar or not polar. So I'll see you in the next video.